This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, good. Thank you all for having me here. So the title isn't covering the evidence for perceptual decision making, but it's really sort of just a focused investigation on sort of neural representation of objects mainly. But also what I'm going to later do, switch gears and look at a special class of objects, foods, which is interesting. Like this is I cross paths with Stefan because we both get interested in certain things about the same time. Neural sort of decision-making process. I was excited. I had a model. I think we were back to back in an ACNS session. We're like, yeah, you. We do it very differently, but we both love each other's work. And then about 2 years ago, I started getting inspired by food stimuli and start digging into it. And then sure enough, Stefan's already sort of in the area. He already taken an interest in this area. So he's my Melbourne counterpart. Okay. So life is just basically a whole long sort of series of decisions. Really, our days are just basically a cascade of decisions. And to foreshadow a little bit of the work I'm going to talk about later, there's a very interesting study that showed that just for foods, people make over 200 food decisions each and every day. There's an interesting backdrop to this because I had a student present this work in an honors seminar, and he got a very high mark because he actually did some extra digging. The author of this guy turned out to be a massively discredited fraud, but this particular paper was not on the fraud list. And the way he talks about it in the paper, it sort of just makes sense. Like, we get a little hungry, we think about food. We have to think about sort of materials we need to, make to prepare food. We have to think about, all sorts of things. So, just in the food domain, over 200 decisions every single day. As I said earlier, really, the process of decision making, we can sort of separate into two distinct chunks. And one, particularly in perceptual decision making, is we have sort of the stimulus, and the brain forms a perceptual representation of the stimulus. And then we have some sort of higher evidence accumulating process, and that leads to choice behavior. And my strong focus is on the evidence. If you think about a court case, there's a lot of moving parts, or any sort of decision we make. There's all sorts of moving parts, all sorts of extraneous factors. But often what it comes down to is the evidence. If you have a crappy lawyer and he fails to present the right evidence, you're probably going to lose the case. If you have an outstanding lawyer that brings in all sorts of new evidence, you're probably going to win the case. So what the evidence is for perceptual decision making has been an extreme focus, and then sort of making that link to the sort of evidence accumulation process. There's a lot more work on this side, and I think it's really sort of fascinating, wonderful work. But I like to stay on this side. In fact, I can't remember the citation, but Mike Shadlin actually had a paper where he basically, in effect, said the evidence is sort of boring. It's static, and it's really the action is all on this side of the equation. But I don't think so, because I think we have to know about this in order to get to this. Okay, so how can we leverage neural decoding methods to understand decision making in the brain? So I'm going to divide this talk into two parts. One is basically we talk about neural decoding methods and how we can sort of learn about the brain sort of bringing together and forming a representation of the evidence that we're going to use for making perceptual decisions, and then how that flows into the decision-making process. And then part two is going to be all new work talking about food stimuli and its effect on decision-making in the brain. And the rough separation here is this first part's basically going to be old work, sort of inspiration journey, and the second is going to be new work. Almost all of it's unpublished. And I wanted to do something different in this talk here. Usually I spend 15 minutes unpacking how decoding methods sort of work. But I feel like most people have sort of heard that. Daniel can just like, Stefan can just like sleep through it and like, take a nap. But instead I wanted to like sort of, in particular, I think it's good there's lots of ECRs in the audience. I want to take you sort of my journey of the sort of decoding methods and how I got to, and how this journey sort of brought me to this interest in decision making. Okay, so neural decoding and perceptual decision making. So here's a brief roadmap. I'm going to talk about neural decoding methods, something called representational spaces. So I'm thinking this should be familiar to most, but I'll unpack it in a very high level way. I don't want to get into details because I'll slow things down and we've got new data to talk about that I think it's more exciting. Okay, so how did my journey begin? I was actually at the very front end of neural decoding methods. I wrote this paper in 2003. Representations or patterns of activity in categorical representations of objects. Yeah, I can even say the title. And how it got started was basically I had this co-supervisor, Paul Schrader, who was super into machine learning. He was doing it all the time. And I was really inspired by that. And I was doing a lot of work on neuroimaging data. And then I started thinking, we should put these things together, particularly inspired by a paper by James Haxby. But at the time, I didn't have fMRI data, and Jack Van Horn launched an initiative, which I really think is wonderful. It sort of predates sort of open data in that he required all submissions or accepted papers to Journal of Cog Neuroscience for them to submit their data with the paper. So fortunately for me, as I said, there's this paper by James Haxby that's super famous. I'll show it to you in a minute. But they also wrote another paper by Alama Ishai, and they published it in Journal of Cog Neuroscience, and they had to submit their data. And so I got to write to the Journal of Cognitive Neuroscience and say I would like a request, and the CD came in the mail. And figuring out, because things weren't organized, figuring out all that was a big mess, but we managed to do it. And on top of that, Jack organized a competition for data reanalysis. So I entered this sort of competition. So I was super excited. I was like thinking about brain representations, machine learning, neural decoding. PhD is like the best time. So PhD postdocs are best time, best thinking of your life, because you're just basically wandering around, sort of in the clouds, thinking big. As I said, Paul was the guy driving a lot of the machine learning into my head. I sat him down many times, like, no, Paul, explain this. By the way, I have no background in mathematics. Really, most of my sort of machine learning decoding methods came from me forcing Paul to explain what things like classifiers do to a layman's person, and then sort of looking at graphs and testing things, and then sort of figuring it out, a good intuition of how they work, and then applying them. So we did this paper and submitted as part of the competition. At the time, my supervisor, Sheng He, who's a really brilliant but very stern Chinese man, he was like, "Meh, Tom, why are you working on this stuff? It's going nowhere. Just drop it." So he was pretty much detached from the whole project. Fair enough. And indeed, we actually got third place, I think, out of 6 submissions to the data reanalysis competition. And that's not, I don't think that has anything wrong with the ideas there are. I like to take it on myself because this is perhaps the poorest written paper of my career. It is terrible. Do not read it. It's incomprehensible. The ideas are actually really good, and I'm going to tell you a little bit later how one sort of links up to sort of future stuff. But you just don't read it. Okay. And the same year, a much better written paper came out from Cox and Savoy that really sort of explained the methods and did a better job at sort of explaining their importance for sort of advancing things in cognitive neuroscience. But if you really want to go historical, this was the key. This was the starter right here. This is the paper that got my brain sort of thinking every single night for months about like neural decoding methods, representational spaces, all of it. Okay, so decoding methods were sort of tickling in the background, and they really hit it big when this paper came out from Kamatani and Tong. By the way, I'm going to show you some slides with data. Don't feel like you have to understand everything that's going on in the slides. I'll just sort of talk over the big picture stuff, because it's more just sort of the idea of the path that I'm trying to go through. And why was this a big deal? Well, basically, what they showed is you can decode stimulus, the orientation of a grading pattern in visual cortex. But fMRI resolution, so if these are voxels, take like 3 by 3, at least at the time, we'd have a bunch of orientation columns that's indicated by the color here. All these things would sort of, the idea is all these things would sort of average together. A voxel doesn't have access to an individual orientation column. So how on earth can we decode the orientation of stimulus if our voxels are too small? This should sort of just be washed out. And what Kamatani and Tong basically argued was that there are going to be little tiny biases. So each one of these voxels is going to have a smaller number of different orientation tube neurons, but there's going to be really teeny tiny biases. And our machine learning classifiers are so good that they can use these biases to decode the orientation of the stimulus. And that's what got people really excited. They're saying machine learning gives you subvoxel resolution in fMRI. And that was sort of, everybody really jumped on board then. Toolboxes were being things, basically anything that had decoding was being published in Nature or Current Biology. I don't think I've ever published in any of these journals, not with neural decoding methods. No, I was always sort of somewhere in the background. Anyway, they were so good that even my supervisor was impressed, and he started adopting these methods in his lab. But to be fair, I have to say, Zheng was a stern Chinese man, but he was also very smart. And he didn't actually buy the story of subvoxel sort of resolution. He's like, there's just something wrong with this. I just don't believe it. And that sort of seed sort of always percolated, and I'll sort of circle back to that a little bit. Okay, in 2011, I moved to the University of Maryland, and fMRI is always expensive. I'm always trying to get the data for free. I don't like paying for it. I'd rather hire a postdoc than pay for the data. And when I arrived at the University of Maryland, yeah, okay, there was an expensive fMRI scanner, but there was also an MEG system, and a professor named David Popple, who said, hey, play with my toys, they're free. I won't charge you anything. For anybody who does MEG, typical MEG session will cost you about $1,000 per session. So that's great. I'm like, cool. I don't have to pay for it, and I can just sort of switch fields. So I just take my toolbox of neural decoding methods, and I start applying them to time series data. And again, you don't have to worry about the details. I'll tell you about the big picture stuff on the slide. So the first study, basically, where I love faces, and I was thinking about object invariance. And I was basically showing different categories of objects in different regions of the visual field to investigate at what stage of processing do we have sort of invariant, spatially invariant representation of an object. But as part of the analysis, I built a little model that basically was looking at, like, okay, so if we shift, these little sort of moons are the position of the object on the screen, can I take the area that's sort of non-overlapping, because the area that's non-overlapping would be the differential activity in the cortex, if I'm looking at the sheet of the cortex. And that's these sort of little gray areas. So can I just do a little model and predict to see how decodable the stimulus is based on this non-overlapping area? And that's what's sort of shown over here. It was like a beautiful correlation. I think it was like 0.92 or 0.93. One of my other colleagues in psychology in Maryland was like, wow, that's like a physics-like result. You don't get that. You don't get that in neuroimaging and psychology. So that's really great. That's wonderful news, because that tells us something very important and fundamental when we're thinking about data, and that is decodability directly relates to the information encoded by the system. Right? We can use decodability sort of measure sort of how different things are represented in the brain. It's a simple assumption, but it's an important one to sort of confirm. And we do that with this model here, a simple model. This only applies to visual cortex. That's okay. All right. So now, at this point, things become to unravel a little bit. And we go back to Kamatani and Tong. So as I said earlier, Kamatani and Tong's original explanation of how we could sort of decode subvoxel resolution was that the number of orientation-tuned neurons in each of the voxels can have slight differences, and the super smart machine learning classifiers are sort of summing all these differences and able to sort of decode the orientation. And I was doing something in a related project that sort of forced me to build another model. So I just built a model where I just go kind of completely against the assumptions of Kamatani and Tong. And also, there's another explanation for orientation decoding I'm not going to talk about. But it's also about biases in the voxels. So what I did is built a model that says, what if I make my voxels completely unbiased? So there's an exact number of orientation-tuned neurons in every single voxels. There's no biases at all. Can we still decode from this representation? And that's what this is here. Again, you don't have to worry about the details of the figures. It's basically just sort of taking all an orientation stimulus, horizontal, running it through a bunch of filters that correspond to different sort of V1 neurons. That generates a map, and then that generates a response that we would see for any given voxel in the fMRI pattern. The key thing is, both currently explanations assume it has something to do with biases in the number of voxels, by orientation to neurons voxels. And what this work basically showed was you can still decode even if you have no biases in the voxels. It turns out that there's this sort of interaction between the edges of the stimulus that create like a cortical artifact. Creates like a little halo, a shadow, if you will, in the sort of activation map. And this figure sort of explains it, but it's basically if we have an orientation to neuron and we sort of apply it to the edges, we get this little sort of halo-ish figure, and that's what these are here. These are the sort of halos that you would get from different orientations. So vertical, tilted 45, 90, 135. You can see that sort of the halos are sort of different for each of these stimulus. The really cool part was not only does that show that you can sort of decode orientation without having any biases, but actually these sort of maps that come out are exactly the prediction of the countering theory, of the maps that you would expect to see from the countering theory. So really we sort of almost explain two theories at once by sort of chucking the explanation that there is biases in the cortical map. And this was later, so that was all just a model. Went to Journal of Neuroscience. They demand, or one of the reviewers said they want fMRI data. I wrote back like, come on, that's a lot of work. That's expensive. And that reviewer said, yeah, fair enough. And then subsequent work, actually some by, it's interesting when postdocs kind of end up countering yours, but Susan Wardle did an experiment trying to sort of show this was true, and we didn't find good evidence for it. So we're kind of like, oh, well, maybe we're wrong. Okay. But then Miriam, Elijah Miriam, largely spearheaded this, this lead author, Roth, basically found a better way to test it and really nailed it home. They confirmed that, yeah, it's basically this edge artifact that explains orientation decoding. Okay, so why am I talking about this old ancient history? Because basically, when you throw a classifier at neuroimaging data, it's going to use all the information available in the data. But often we don't know what information is available. Like even if we take the example of a V1 map, where we know a boatload of information about how things are represented, it was, what, Kamatani was 2005. it was almost 10 years later that I did my thing where I sort of showed that the model can explain it. For 10 years, they had sort of, they weren't sure which theory. And by the way, my theory still could be wrong. The main thing that I'm trying to point out is like, even in an area that's really well known, we don't know how decoding sort of arises from the maps, unless we're really sort of thinking strongly and hard about it. So that's a very bad thing. And it just gets worse when we move to things like objects in IT, because then we don't know what the neurons, or we know less about what the neurons do. And then like the frontal lobe, that's like the wild, wild west. I don't know, it's crazy. I don't like to think about the frontal lobe because it's just too scary for me. Okay, so that's the bad news, right? Okay, well, we're just going to put a pin in that. We'll circle back to it in a few minutes. Okay, so now let's talk about representational spaces. As I said, I had this really badly written paper in 2003. Do not go back and read this paper. But my thinking at the time was really pretty good, because I was really thinking about sort of activation spaces and things like that. But I think Nico Kriegesgård next leveled it, and I'm not saying I foreshadowed Nico's work at all. If he was smart, Nico didn't read this paper, probably would have confused him and sent him in the wrong direction. But what Nico did was basically did the study where he showed 92 objects, and then he sort of just measured how different all these objects are in activation space to create this. I'm hoping many of you are very familiar. It creates this sort of neural similarity matrix. It sort of shows, red means they have different activation in this map. Blue means they have similar activation, and what you can see is basically all the animate objects show similar activation. All the inanimate objects show dissimilar activation, highlighting the difference between animate and inanimate objects in the cortex. And this is just an MDS flattened figure. It's just a nice dimensionality dimension technique that sort of emphasizes this. So you can see all the animates on this side of the picture and all the inanimates on that side of the picture. And the distance between the pictures indicates sort of decodability. Going back to sort of decodability tells us about the cortical representation. Right, so this is actually amazing news. And by the way, I am not going to circle back and sort of discredit Nico's work. This is genuinely amazing news, because basically we can use decodability to reconstruct brain representations. And this is still probably one of the most fantastic tools in cognitive neuroscience. I also like to always mention, give credit to Kiani in 2007, because he sort of started the work. Nico really fleshed it out and made the beautiful the methods and sort of formalized the framework. But Kiani, using single unit recording data, was the first person to say, hey, I'm going to record a boatload of data from a bunch of different stimuli, and then I'm going to use that to look at representations. All right, so this is great. I jumped on the train. I was doing my work with MEG. I jumped on the train. I basically did something very similar, where I just threw it in MEG. I had animate, inanimate objects. I had this sort of structure, human faces and such. I guess you guys are many at ECRs. You probably wouldn't have been here at the last time, but I showed this movie. But you can basically now, instead of looking at Nico's picture, which is sort of static, what it looks like in IT, you can look at sort of how this representation sort of unfolds over time. So 120 milliseconds, you can see that actually 120 is not a good example. It's not quite there. I think it's about 140, 160. Yeah, you can sort of see the replication of Nico's result, where all the animate objects are on one side, those are the colored dots, and all the inanimate objects are on the other side. So we get to see that whole sort of processing dynamic for object representations. So now we have Nico's method sort of extended, and I call this representational dynamics promiscuity, because basically I think that's about time I came to Australia, and basically I was sleeping with anybody who had a good theory. So I worked with Elizabeth Redkay, like looking at the representational dynamics of social cognition. I worked with Bill Thompson, Simon Carley, and Narayan Sankaran, and on music perception. We did auditory objects. Like this is the same thing as regular objects, except for how, you hear a bus. So it starts with sound waves. You decompose that, and eventually it becomes a bus in your mind. We did emotions, showing pictures and how the dynamics of motion representations unfold over time, and also high-level perception of objects. So, when you get to the representation of cat or human, boat, and things like that, what's after that? There's these sort of things that are sort of higher order things that are like, does this thing have agency? Does it sort of have control? Does it have thoughts? Does it have emotions? And then we just looked at sort of how that sort of next stage of object processing unfolds over time. The particularly cool thing about this paper is the best explanation for how the brain represents high-level object is human similarity. Basically, monkeys are very similar to humans, so they're sort of close to humans in representations. Bugs, they still move, but they're not so human. And then things like, other objects and things like that. There's a funny anecdote with sort of ethics. Like one of my first professors, Dwight Burkhart, he studied salamanders' retinas, and I asked him, why salamanders? And he's like, they'll let me do anything to a salamander. Like, really. Nobody cares about salamanders. I have fundamental questions about the retina. I don't need to be slowed down by ethics. So, yeah, I just study salamanders. Okay, so salamanders would be far away from humans in this sort of domain, so humans don't care. If you want to do cats, that's another level of difficulty. If you want to do monkeys, that's another level of difficulty. If you want to do humans, that's a level of difficulty still. All right, now it's time to, oh my gosh, I probably forgot. So as I said, there's this sort of problem that machine learning classifiers use all the information, sort of illustrated by this figure here. And there might be multiple sources of information. We could have, biases and voxels, edge artifacts. There's the real representation of the stimulus. Could be anything. Like one good anecdotal story that I heard from a professor at UCL was he had a postdoc that had these amazing, amazing results, and he didn't believe it. And they sort of dug into it for months and months and months. Basically what was they had like a semi-structured thing over time in their sort of fMRI sequence. And the classifier was using basically X gradient drift. If you know fMRI, there's like this little drift that's always present in fMRI. I think it says it heats up. Is that right? It doesn't matter. But it's always present in fMRI. But basically the classifier was sort of figuring out, hey, these sort of events happen in a certain order in time. If I just use the X gradient, I can actually predict what's going on. So it had nothing to do with any certain condition. So you have to be very sensitive to things. But in cognitive neuroscience, we want to know, what information is, quote, represented. And I say even better, what information is used by the brain. So how do we sort of disentangle this? And this is, we'll just go try to figure this out. But this is just one way of thinking about it. In 2016, a guy named Lee DeWitt wrote a really nice paper about information processing and cognitive neuroscience. And he really sort of nailed this point in particular. And he basically said, you can't simply measure something like electrons or firing neurons, or whatever, and assume that you've measured information. To basically show that you've measured information, you have to basically construct a model of how that information is being read out, a biologically plausible model of how that information is being used. And then you can sort of narrow the scope and say, hey, I got a model of how it's being read out, and now I can be more confident that this is actual sort of information. Excellent paper, by the way. And really this amounts to basically shifting our perspective. And I think the early years of sort of decoding are characterized well by this, in that sort of we become egocentric neuroscientists. We just think about what we can decode, what we can decode, what we can decode. But that's not, but if we want to know about information that's being used by the brain and represented, we have to think about the brain as a decoder. There's a quite famous book, I think it's called Spikes, where a similar argument is made in the neurophysiological domain, where they're always pointing out is like they use average spike rate to measure a lot of effects in monkey physiology. But the downstream neuron does not get average spike rates. It just gets spikes. So we shouldn't be sort of characterizing our data using average spike rates. We need to actually build a model for that of what that downstream neuron is receiving, and then we can move a step closer to sort of how information is sort of flowing between areas in the brain. Okay, so I did this in like cartoonishly simple fashion. Actually, before DeWitt wrote his paper, it was just sort of something that I was sort of thinking about and turned out sort of worked pretty well. A couple of undergraduates. But basically what we did was we sort of go back to that sort of decodability relates to the representation. And so if we just say, you know, we sort of assert that that distance between things is a measure of neural similarity, but it's also going to mean things that are more similar are more difficult to sort of decode, but they're also going to be more difficult for people to categorize in behavior. So basically, you know, if we have this picture of the representation from Nico, we should be able to tell how difficult it's going to be for people to make judgments based on how far they are apart in that map. And then we just sort of extend this into signal detection framework, where you sort of change all the animates and inanimates to dots, and then you project it onto a plane, and then you can say basically the further away from this line, the harder it is to make the choice. And it's that simple. All right, we did this, more free data. We got some data off of mTurk, and then we confirmed basically that prediction that indeed distance, we call it distance from the bound, can actually predict sort of choice behavior, reaction time behavior. It's not perfect, it only works for animate objects, still sort of trying to figure that one out. But it's a really crude, it's a really cruddy model, but it sort of works. If we port it to that sort of next level of decision making, then we can do things like explain the reaction time invariance. Wonderful. I think a lot of this was part of my future fellowship, and I think a lot of it was part of a subsequent grant, but I think the thing that some decision people liked about it was I was actually like, I'm agnostic about what happens over here, but it helps explain your data, so it's great. And I think that's why they really liked it. And then this subsequent work by my former postdoc and PhD student, Tyler Grutzwager, basically used what they call searchlight analysis. It's like finding information in the brain, multivariate information in the brain, with also using our sort of model. So there's two searchlights going on. The first searchlight is like finding areas that we can use decodable information to separate whether it's an animate or inanimate object. And the second is a searchlight saying, okay, what areas of the brain can actually predict the reaction time decision behavior. And what you can sort of see, have I gotten this far without a pointer? I guess I have. Is the orange is where you can decode animacy. So there's lots of orange in these maps. So there's lots of areas that you can help separate inanimate objects reliably. But the amount of red areas is probably about maybe 30% of that, maybe even less. And the red is the areas where you can actually predict the sort of behavioral outcome of the task. So we can sort of constrain the areas, not just because they have information, but they have information that predicts behavior. And that sort of prediction comes from that readout model. By the way, I strongly emphasize it's not, there has to be a better model than that. It's just a really simple model that sort of takes a step forward. Okay, so this is good news. We have a very basic model of neural readout that sort of helps. It helps. Doesn't solve these sort of interpretability issues. And it works for MEG too if you want to do that. And EEG too. Okay, let's move on to foods. I think I swore I was going to be fast in that first part because I want to see you guys the whole historical journey. But I think there's good lessons in there. And actually, when I wrote this talk, I was sort of, I turned 50 this year, and I'm like, hey, I get the floor now to sort of go like, I'm going to take a happy journey, and I'll try to teach some lessons to the UCI. So that's what I tried to do in the first part of the talk. Okay, so now.
You still have 10 minutes if you want, by the way.
What's that?
You can have 10 more
Oh yeah, I'll drone on forever. You guys can wander off. It's fine. I'm having a great time. Okay, so we started to get interested in foods and collected boatloads of data. All of it's unpublished at this moment. So it wasn't me just sort of reminiscing about my career. I actually want to tell you something new. Okay, so a couple of years ago, I got invited to review this paper on food stimuli, and it just really sort of got me thinking. I'm like, wow, foods are probably, some people would argue faces, but foods got to be the coolest stimulus for the brain. Really? I mean, like, can you get any better? So you just think about it, broadly. It's like, there's of course like homeostatic regulation things, emotions, man, like some people are passionate about foods. Any Italians? You're angry. All right, foods tied to memory, like people will strongly associate food with like sort of memories. I ate this food at this restaurant, things like that. They're multisensory, so we got sort of multisensory integration. All perception, all the sort of perceptual units are sort of, working. And of course, decision making. And decision making is basically just completely gone haywire. We have an obesity crisis because food used to be something we have to hunt and gather. But now, instead of it being sort of something we have to do, it's something we have to make decisions. And it's not even the choice now. It's usually just what to eat, not even just can we eat. So I just love this sort of as a topic, and the more I think about it, it's linked to nutrition, social occasions. We're going to go have some food later, and we'll all sit down and have a good chat. And it's also quite personal. Like some people hate lobster, other people love lobster. I'm going to show you a picture of Spam in a few minutes, and I was quite surprised. Like to an undergraduate, I'd be like, "Who likes Spam?" And I thought, crickets. But apparently, there are some groups that still enjoy Spam. And I'm like, fair enough. My parents used to feed it when I was young. And the also interesting thing in the vision science literature is they've been looking for a food area for a long time. Sort of like they found the fusiform face area, the parachemical place area, the body area, but they couldn't find it, which didn't make sense because, it's like with faces, it's up there in terms of ecological importance. Why, people have made arguments that the cones in the retina are organized for primates to basically spot fruit in trees. So why is there no sort of dedicated module like you see for faces? And the short answer is they've sort of now figured out that yes, there is some specialization in visual cortex for foods, but it's much more diffuse and it's variable across participants, and that's because, or the argument is because faces are they're all bowling balls with two eyes and a nose. It's sort of easy for the brain to sort of tune in to those features. Foods are highly variable. You can't sort of very simply tune into features of foods because it's basically all features. It could be a circle, it could be orange, it could be a plate of spaghetti. Like you can't just have a single feature to find a food. So this is very exciting that now, they're starting, hey, there's actual cortical representation of foods. Okay, so we started with these studies basically saying how do humans sort of discriminate between foods? So some options are color, shape, texture, taste, smell, properties like healthiness and calories. But then there's also the extra factors like how appealing you find the food, or how it might even be modulated by how hungry you are at the moment. So we use this really cool task developed by Mark Habert called the tripletask. It's sort of a covert task where you have people choose the odd item out. You show 3 items and they say which item doesn't belong. And the items are all very randomized. But the key is each time you make a decision, which one's the odd one out, you're saying something about the similarity of food. So in this one, it's super obvious. We have a steak, hamburger, and some almonds. Almonds are very much the odd one out. It could be these are sort of proteins and these are nuts, but these obviously cluster. But if you do this over and over again, you're going to get into sort of cases where there's more subtle distinctions, right? You have 3 different fruits where you have an apple, orange, and a banana. And then shape is going to start to sort of form it. And in other trials, taste is going to start to sort of dribble into the decisions. So the cool thing is, it's super, first of all, the bad thing is, it's super data intensive. You need tens and thousands of trials. When Martin did his original one, I think he had like 1.3 million trials. It's data intensive, but the good thing about this task is because it's unconstrained and you don't know what's happening on any given trial, people are going to use different aspects of the foods to, of the stimulus to make the choice. And that really is able to give you sort of a more complete space of all the different things people use to make these, to discriminate among foods. And the other thing is sometimes factors are going to compete, like maybe you have two dinner foods and breakfast foods, but one of the breakfast foods and dinner foods taste more similar. And then you have to choose whether it's what time of day you eat it or the flavor. So they're going to compete, and you can also sort of rank like what is important for the foods. I would try to avoid this. Is basically another similarity matrix like Nico's, but don't worry about it. But basically what you can see in this matrix is natural foods clustered together. People treat natural foods as very similar from prepared foods. Brussels sprouts and pumpkin are more similar than fries and salami. That's one of the major things that discriminates. We can take this, say, how do different factors explain this data? And basically this is what it comes out. Perceived transformation and naturalness are very similar. It's like how much work has been done just to get this food ready. And naturalness is like, apple, it's ready because you can just bite it. But if you have like sort of a raw piece of ham or something like that, that's going to take a lot of sort of work and things like that enough to prepare the food. So naturalness and perceived transformation, calories, obviously have some explanation. Arousal, immediate edibility, like how much work it's going to take to sort of get it ready for you to actually eat. But interesting, like all these sort of visual factors really don't contribute much to it. So luminance, the shape, color, and contrast, they don't really weigh much into our sort of how we sort of discriminate on foods. So we have this nice task now that sort of tells us, on a very global level, how people separate foods into different categories. We can also play around with this using things like dimensionality reduction, and when we do these things, it seems like natural and prepared food seems to be like one of the major distinctions. Interesting, like here, this is, I don't know why it's classified as natural in the database, but that actually looks like cooked lobster, which I would argue to be a prepared food. All right, so let's talk about some new neural data. So we went and did an MEG study, and we had people look at the foods in two different sort of tasks. One is sort of a fast viewing task where they're doing a task at fixation. They're looking for that little bullseye. These are like super rapid. It's a really nice, hyper-efficient method developed by Tyler and Amanda, my former postdocs. Allows us to collect boatloads of data in a very short period of time. And then we also had a categorization task where they're shown foods and then they respond, is it a natural or prepared food? And I will just sort of look at basically what happens in the brain when they sort of look at these stimuli in these different contexts. Okay, so if we take that behavioral RDM of how people sort of discriminate among foods and compare it to the EEG data, we get a really sort of nice fit of data right about 200 sort of milliseconds, which is actually pretty quick. There's a lot of complexity in that sort of high-level representation of foods, but it happens very fast in the brain. So clearly the brain's like tuned in, it's able to extract that sort of high-level information very quickly. The other thing is that's true even when they're not paying attention to the task. This is the orange line is when they're doing the fixation task. So they don't even have to look at the stimuli. The brain's very automatically processing the stimuli, even though they're not paying attention. The blue is when they're actually performing the task, and you can see the response is sort of, decodability is much more extended over time. So when we engage with the stimulus, you get a lengthening, a drawing out of the representation. By the way, you cannot compare these two things in terms of height because the fast stream has way more trials because we're sort of, brrr, so we get like, 70 trials per banana with fast streams, but we only might like get 10 trials when they're doing the categorization trials. So part of that correlation is basically just power in the data. But you can sort of look at the shape of these curves, and you can sort of see how the passive has a very punctate response, but then drops down in chance, while during categorization, there's sort of a slower rise in extension. We can drill down to individual factors. And here, the data is relatively, it becomes much more noisy because we're sort of drilling down deeper. Well, basically, we can see that sort of naturalness and perceived transformation, and even to some extent edibility, much like in the time course. Let's see a break there, being represented later in the stimulus period. Look at calories and perceived calories. The interesting one about this one is seems like perceived calories is a better fit to the data than real calories. So there's some foods that trick people. Avocados are number one. A lot of people think avocados are, they're nice, healthy foods. They get boatloads of calories, and they're super, but they're really good, healthy fat. And I'm actually told that sort of, sometimes when they're working with anorexics, that's one of their sort of key foods, because you can almost trick them a little bit and say, hey, have an avocado. And it's really good, healthy fats, and it's lots of calories, but they believe it to be low-calorie food. And then we can look at sort of the emotional, how emotional valence is. But the evidence is still pretty weak for these. Okay, can we go back to that model? Remember earlier, it was like we want to sort of link decodability to actually behavior. So in the EEG, they were saying whether they thought it was a natural or transformed food. Okay, first of all, we do decoding, naturalness versus transformed. We can do that, no problem. See, again, we can see that decodability is affected by the observer's attentional state. Basically, when you're actively engaged in the stimulus, there's more extended representation. And indeed, we can predict the RT data using distance to bound. The two sort of scale really similar to one another. When you sort of look at it, like, wait, is that the same plot? Did I do the same figure? Did I copy that? No, they're actually different, but they're very strongly related. But the other thing to point out here is in terms of sort of the predicting representation thing, is you can see it works also when they're not paying attention to the stimulus. So what that tells you is sort of that representation, that information that is related to, that can sort of predict the future behavior, they don't actually have to engage in that behavior to sort of measure that representation. They can be doing something else. It's a very automated process. And this is seen repeatedly over and over and again. When I originally did the analysis with Nika Kriegelskirt's data, they were doing a task that had nothing to do with the stimuli. And a lot of the studies we do with this distance response, they're not actually engaging the stimuli. So it's very, often we're looking at a very automated representation of the stimulus that sort of can directly predict future behavior. It's a subtle point, but it's one worth making, is that sometimes these things can be contaminated because they're actually doing the behavior. But what this shows is even when they don't do behavior, that core representation is still there. All right, how are we doing? Okay, I can motor through. All right, finally, the last one, does hunger affect our evaluation of foods? Yes, it does. I'll move forward. Doesn't seem to affect decodability, but we're still working on it. There's some evidence there might be something there. I'm doing this cool stuff with David Lay about serial dependence. Basically, long story short, if you see a pizza, basically the next food you're also going to judge to be a little more high calorie because there's sort of this carryover in judgment. Stefan can tell you all about that stuff. He's more in his wheelhouse. And we're also playing with these things. These are also behavioral ones sort of by manipulating people's sort of context. These are all behavioral studies that we're trying to basically get sort of nice behavioral effects so we can get into neural data. All right, here's the summary. Decoding is powerful, but we have to be sort of mindful, number one. We've got a whole paper on that if you're interested in. Measuring information is challenging, but making a model, I think throughout my talk I've showed models are really good because they make your assumptions explicit, and you often find that that's where the interesting thing. That's how I sort of was unable to figure out what was wrong with the Kamitani and Tong model. And foods are just a super stimulus for the brain. All right, my advice for ECRs, because I wrote this sort of little as a journey thing. So I brought up the fact that my supervisor was uninterested in decoding for a reason. And that's like sometimes you're going to be super excited about things. It still could be important, but your supervisor might be meh. So I say, you know, I'm not saying to ignore your supervisor. Usually their wisdom is there to guide you from not going into holes of, that you can't climb out of. But sometimes they're just be like, meh, if you're really excited about it, you think it's good, you keep working on it. Science is fun, be a great communicator. This is like I'm telling you, the 2003 paper, awful, awful, awful paper. I was more trying to get the paper published because that's what you needed to do.